So let's see, I'm trying to think of what to do next. I don't mean immediately next, but I mean in the remainder of the semester. There's non-abelian gauge theory.
Is there any possibility of you doing conformal field theories?
Conformal field theory.
Yeah. Is it something that is possible, or
that was not anywhere near the top of my list. But that doesn't mean that we can't. All right, I will think about that. I would have thought that non-abelian gauge theory and something about the standard model would be important, unless you've all seen that before.
It would be high on my list, but conformal field theories would also be there.
Okay. And then there's path integrals. I think we should do path integrals unless you've all seen path integrals.
I've seen them, but it doesn't hurt to see them twice. It might hurt to see them depending on how you look at it.
So let's see, what, oh, the renormalization group, something about that. All right, well, we might as well start.
It's recording.
Already?
Mm-hmm.
Oh.
okay.
It's important stuff.
All right, so let me just remind us what we were doing. We were talking about electron-positron goes to muon, mu minus, and I guess I should have written that as E minus and plus, mu minus, mu plus, so that gets to be a kind of crowded diagram. If I erase a couple of parentheses, oh my goodness, this is filthy. So that's the process, and one reason why I switched to this from E plus E minus goes to E plus E minus is that there are two diagrams in that process, and the trace identities are much more complicated. Moreover, this is a process that it's basically the process that's occurring that was done at SLAC in their E plus E minus collider, then was done at CERN in their large electron-positron collider. It was done, if you replace E plus E minus with proton, antiproton, that was done at the Tevatron and at the Large Hadron Collider. And at the Large Hadron Collider energies, you can think of this as quark, anti-quark goes to whatever. And as the energy of the incoming electron-positron pair rises, what comes out the back end can be not just E plus E minus or mu plus mu minus, but can be various hadrons and so forth. And in fact, some of the great discoveries made at SLAC during the, I guess, 1960s, 70s, 80s were by doing electron-positron scattering at higher and higher energy. One real advantage of this process is you kind of know what an electron is and what a positron is, whereas when you're colliding proton, antiproton, you don't quite know what the proton or the antiproton is. It's, okay, you have three quarks, infinite number of gluons, all interacting strongly and mysteriously, and so it's a little bit, ambiguous. Okay, so I think last time we realized that that the sum over S and S prime of V bar gamma A U U bar gamma B V, I think we got to the point of seeing that this was 1 over 2p0, 2p prime 0, and then trace of minus I p prime slash minus mass of the electron gamma A minus I p slash plus mass of the electron gamma B. And for the muon part, there was a similar trace. So this was for the electron. For the muon, one had, let me sort of write it here, I think there's some space here. The sum of, over the spins, plus or minus a half in both cases, for the muon and the anti-muon, sum of U bar gamma A V, V bar gamma B U was a trace of something very similar, minus I K prime slash minus and muon gamma B minus I K slash plus M muon gamma A, and that divided by 2k0, 2k prime 0. So we also had the trace, we learned the trace identities last time, and let me just say that what one gets from putting these together and using the trace identities is 32 P prime K prime PK, these are dot products, plus P prime K PK prime plus mu squared PP prime plus me squared KK prime, all that, and so that's the trace, and then we have to divide by 4p0 prime 0. So that's the spin sum, basically, of the electrons. For the muons, one gets something similar. And as I said, this is after one uses the trace identities that we derived at the end of the last hour. I latex these notes up, and they're on the website, the class website, so there's a little more detail if you want to check this, but I thought that to avoid going blind from writing down the details, I would skip some of that. So this M is this, and what we get then is that 1/4 the sum over S and S prime of absolute value of M squared is then e to the 4th over e to the 4th over 2 pi to the 6th, and then P0, P prime 0, K0, K prime 0. And then what's up here is P prime, K prime, PK. Let me just mention, the mass of the electron is very small. It's half an MeV. The mass of the muon is 100 MeV. These things occur squared. And there's a considerable simplification if you just set the mass of the electron equal to 0. If you're at an energy at which you can produce muons, then the initial beam of electrons has to be at least 105 MeV against 105 MeV. And that means that the mass of the electron is 1 part in 200 of that. And when you square things, it becomes completely invisible, but it occurs in all sorts of square roots and algebraic identities. And so we will spare ourselves the care of keeping track of it. So this is then P prime dot K, P dot K prime plus mu squared. Oh, wait a minute, I'm just repeating that. Well, yes and no. Actually, if we do keep the electron in this equation, it's still simple in this equation where this is P plus P prime squared, that's Q squared. So that's the 1/4 sum of M squared. The definition of M that I'm using is the one that Weinberg uses. Peskin and Schroeder use a slightly different M. One is proportional to the other, but I forget what the factors are. Okay, now, obviously, if we're talking about a colliding beam experiment where you have E plus or E minus, E plus colliding, and then mu minus goes out some angle theta, that's the scattering angle, and it's obvious that you would use as your coordinates, you'd use the rest frame of the collider, which is the center of momentum frame. So Q squared, which is then P plus P prime squared. Well, P plus P prime is just the 4 vector 2e comma 0 squared. And when you do the Lorentzian product, that's equal to minus 4 e squared. In fact, I see now I wrote it as plus 4 e squared from some. So this is minus 4 e squared is actually correct. So there's going to be an overall minus sign. I don't have to change in the notes. The cosine of the scattering amplitude is P dot K. I'm sorry, P dot K, but divided by the length of P and the length of K. So that's another typo. Cube pencil. Other things that occur here that we need to work out are P dot P prime minus 2 e squared P dot K is E times length of K. In fact, I'm just going to use K as length of K. K cosine, in other words, I'm going to set K equal to the length of the momentum of the final mu minus. This is K cosine theta minus E. P dot K prime is P prime dot K, and this is minus E K cosine theta plus E. And when you put all that together, this sum, 1/4 sum over spins, and this was actually SS prime TT prime. So sum over all, the computation is much simpler if you don't try to compute the cross-section for specific incoming spins and specific outgoing spins, and in most cases you can't measure them anyway, or don't measure them anyway. And so what one does is one averages over incoming spins, that's 1/4, and one sums over final state spins, that's well, one just sums over them. And in that case, this thing becomes e to the 4th e squared e minus k cosine theta squared plus e squared e plus k cosine theta squared minus 2 m muon squared e squared. And as I said, I'm neglecting the mass of the electron because it's very small compared to the energies, the mass of the muon and to the energies that would be relevant in such experiments. And of course, at the large electron-positron machine in Geneva, when they were running it at such that each electron had an energy that was 1/2 the mass of the Z0 gauge boson, so that they were sitting on the resonance of the Z0, and so the process was E minus plus E plus, and it would go to a photon or a Z0, and then to whatever came out. And that would be, what came out was every charged particle that had whose mass was achievable at the energy they were talking about, which was around 90 GeV. And so each beam was 45 GeV essentially. So this is then, maybe I'll skip a couple of algebraic steps. One gets to e to the 4th, and then it's e squared plus k squared cosine squared theta plus mu squared. And then one divides that by 16, still is 2 pi to the 6th, and e to the 6th. So that's 1/2 the sum of the m's of the matrix element squared. Now, what is this? This is, of course, the S matrix amplitude. Probabilities are absolute value squares of amplitudes. And so the squared amplitude is then 2 pi squared delta 4th of p plus p prime minus k prime absolute value squared times this thing, which is where all the complexity lies. 1/4 the sum over all spins of the absolute value squared of this matrix element. Now you might be a little anxious about the square of the delta function, especially since the delta function is evaluated, delta function preserves energy and momentum conservation, or conserves energy and momentum, and consequently, it's delta of 0, which is infinite. Well, the idea is that use the identity delta force 0 is an integral d force x over 2 pi to the 4th e to the I 0, which is say 1. And so this is all of space, all of time divided by 2 pi to the 4th. I must say that in the new building, the one thing that I hope will be an improvement is that the chairs will not squeak. The secretary who chose these chairs and the chairman who supervised it, I think it was a nice woman, but not very smart. Anyway, so this is what we use at this stage, and so our probability then is Vt for one delta function. We're left with 2 pi squared, another delta function that we want to keep, p plus p prime minus k prime, and then 1/4 sum m squared. And now we have been dealing with all the particles and fields in a continuum representation. And as we make this transition to regarding delta force of 0 as being Vt over 2 pi to the 4th, we also want to change our normalization from delta cubed of p minus p prime to this same volume of some, so we're essentially putting the universe in a box, and now we're going to use Kronecker delta as the normalization of the states. And the probability of the process happening is then we change the normalization, and we have to do that 4 times. And so we have 2 pi cubed over v to the 4. 4 times because there are 2 initial state particles and 2 final state particles. And then we have s squared, and then we have the number of final state particles. So that's our computation for the probability. And this number of final state particles is v over 2 pi cubed squared d cubed k prime. So basically, this is just the rule that you learned in statistical mechanics, that the number of particles that can fit in a phase space volume of so much momentum, so much volume, you divide by Planck's constant cubed, and Planck's constant in these units is 2 pi, because h bar, which is Planck's constant over 2 pi, is set equal to 1. What I'm doing here, by the way, in a very abbreviated way, is relying on the material that Weinberg explains in Chapter 3. But I'm just taking out the parts we need rather than going through the whole of Chapter 3, which would take, well, if we were doing it in detail, it would take a couple of weeks at the very least. So what we've got now is that the rate in which probability is being produced, which is P over T. And so we're dividing by this time of the, we put the universe in a box of space and time. And so this is then 2 pi cubed over V to the 4th to change the normalization of the states. Absolute value of S squared, we're dividing by time, multiplying by NF. When we include this NF factor, what we get is that the rate is 2 pi cubed over V to the 4th, S squared over T, V over 2 pi cubed, squared d cubed K, d cubed K prime. And what this boils down to, I'm going to skip a couple of steps here, but they're latex and on the class website. It's 2 pi to the 4th over V, delta 4th of P plus P prime, minus K prime, 1/4 sum M squared d cubed K, d cubed K prime. So that's our rate at which probability is being created in this process. Now, what's the cross-section or the differential cross-section? Well, d sigma is this structure divided by, is the rate divided by the flux. And we'll write F as flux. And what's the flux? Well, the flux is the relative velocity of the particles divided by the volume. And the relative velocity in this case, since we have an effectively massless electron approaching an effectively massless positron, both of them moving effectively at the speed of light in the rest frame of the collider, what one has is U is equal to 2. So this is equal to 2 over V, C being 1. And so then when we do this, what we get is 1/2 2 pi to the 4th delta 4th of P plus P prime minus K prime, and then times 1/4 sum of M squared, and then d cubed K prime. Well, this last delta function is a 4-dimensional delta function, but if we integrate over d cubed K prime, then that just sets the momentum of the final state anti-muon equal to minus the momentum of the initial state anti-muon. In other words, it sets K prime vector equal to minus K, because this is a momentum 0 frame. That's the frame of the collider, assuming the collider, if it's in California, is being overtaken by forest fires. Today. So what we get then is that the cross-section, d sigma is rate over flux. This is then, I kept writing it in this way in the notes, 1/2 2 pi to the 4th. All that's left of our 4-dimensional delta function is delta of P0 plus P prime 0 minus 2K0, since the momenta of the final muons are the same, and then 1/4 is some m squared, and then what's left is just d cubed k. And this expression then is a half 2 pi to the 4th delta of P0 plus P0 P prime 0 minus twice the square root of m muon squared plus k squared, that k. And then this is 1/4 some m squared, and then this is then k squared dk d omega. And you remember that when you when you have a delta function, it's really simple. If the variable you're integrating over occurs linearly in the delta function, then it's pretty simple. If it just occurs, if this would just had a minus k, then it would be simply, you just had k equal to whatever else was in the argument of the delta function. But here, what we have to do is we have to divide, this is that delta function divided by the derivative of the argument of the delta function with respect to k. And that derivative is k times 2p0 divided by k0 squared. So that's the derivative that we have to divide by. And when we do that, what we get is that d sigma is a half 2 pi to the 4th, a quarter sum of n squared over all the spins. And then we have k squared d omega, and then we divide by this, and that means we multiply by k squared and divide by 2kp0, and that means that one of the k's goes away here, and we get a p0 in the denominator, and that is it. 1/4. Oh, and if we keep track of some of these 2's, what I'm getting, I'm just wondering if there's a typo somewhere here. The final answer came out right, but I was not.
I think you carried a half from here. You put in the F equals U over V over on this other board. There's a 2, but I didn't see it cancel anywhere.
This 2,
Was it? Yeah, did I change it?
that's that.
Is it? I lost track somewhere.
All right, now I'm a little lost. This is what we had, and I've kept the 2 pi to the 4th. We've got a 1/4. When we divide by,
Yeah, I think it's right.
yeah, this 1/2 came from dividing by the flux, and we kept the 1/4. So this is all right, and then when we go down here, we keep all these factors of 2, but we get one extra 2 because of this, that we're having the denominator. So in the numerator, we have 2 to the 4th. In the denominator, we have 1 So altogether, it should just be pi to the 4.
Oh, it's right there.
Yeah, in fact, the notes I think are right. It's pi to the 4th sum m squared kk0 squared over p0 d omega. So that's certainly the final answer. See, do you have a, all right, so let me just. There was an overall factor of 2 and 4 that were puzzling me. In fact, the problem I had when I wrote this up was that when I divided by the flux, I put the 2 in the wrong place in the denominator instead of the numerator, or in the numerator instead of the denominator. And I was off by 4 for a long time. Okay, well now if we plug in for m squared, what we get is that d sigma is I to the 4th, e to the 4th, e squared plus k squared cosine squared theta plus m muon squared over 2 pi to the 6th e to the 6th kk0 squared over p0 and then d omega. And we can pull out some e's, and this means that d sigma is, well, let me skip one step. E to the 4th over 4 2 pi squared e cubed times 1 plus k squared over e squared cosine squared theta plus mu squared over e squared k d omega. And if I skip another bunch of, these are just algebraic steps, okay, the things you learn to do in high school, or if you were educated in Asia, you might have learned them in elementary school and middle school. Anyway, and let me here introduce the fine structure constant, which is e squared over 4 pi. 4 pi, not 4 pi squared. Oh wait, is it 4 pi squared? Now I don't remember. No, it's e squared over 4 pi. Okay, and so this is essentially 1 over 137. This is a dimensionless thing. This is really e squared over 4 pi h bar c. And if we do that, what we get is alpha squared over 16 e squared square root of 1 minus mu squared over e squared 1 plus mu squared over e squared plus 1 minus mu squared over e squared cosine squared theta d omega. Now we have to integrate over solid angle to get the total cross section. And so sigma is, well, part of this integral is easy to do. It's this term integrated over d omega, you just multiply by 4 pi. And so what we get then is alpha squared over 16 e squared square root of 1 minus mu squared over e squared and then this is 1 plus mu squared over E squared times 4 pi plus 1 minus mu squared over E squared times an integral cosine squared theta. Now, d omega is 2 pi d cosine theta. So this is 2 pi d cosine theta. And so consequently, this thing is basically integral of x squared dx. That's x cubed over 3, evaluated at x equal to minus 1 and plus 1. So that's 1/3 minus 1/3, that's 2/3. So this is 2/3 times 4 pi, or 4 pi, 2/3 times 2 pi, which is 4 pi over 3. So altogether, what we get, skipping another couple of steps, is pi alpha squared over 3e squared, square root of 1 minus mu squared over E squared, 1 plus a half mu squared over E squared, when you combine everything together. And E is the energy of each electron. What's called the center of mass energy, and this is the energy that people use when they say the energy of the collider. They add the two together, and so that is 2E. At very high energies, it's clear that these terms mu over E squared, or mu squared over E squared, are just 0. And so the cross-section goes to 3 pi alpha squared over 3e squared. Well, that's almost exactly alpha squared over e squared. Pi alpha squared over 3e squared, as much as pi is similar to 3, close to 3. All right. All right. I think then I'm going to now jump to a different topic, but I'm going to come back to this topic on Thursday. In fact, on Thursday, what I want to do is consider electron-muon scattering and relate it to E plus E minus goes to U plus V minus. The relation is something known as crossing symmetry, and that's something important. And I think it, I'll do that Thursday. What I want to do now is give you a sort of bird's eye view of Weinberg's treatment of Thompson scattering. And so let me, I'm going to follow Weinberg directly now. So what we're talking about here, of course, is photon in, actually I'm going to write it somewhat differently from the way he wrote it. I'm going to have electron in, photon in, electron out, photon out. So that's one process. The other process is electron in, photon out, photon in. And I'm drawing the electron propagator horizontally because we don't know whether those points here as space-time points, say x and y, are one ahead of the other or one behind. We integrate, remember, over d4 of x and d4 of y. So Y could be earlier than X, X earlier than Y, and so forth. And so this is P and S. This is going, oh, I'm sorry, this is K. And polarization vector E. This is P, spin S. This momentum here is going to be P plus K. This is going to be P prime, S prime, and this is going to be K prime, P prime. And so this one also is PS, this is KE, this is K prime, E prime, and this is P prime, S prime. This momentum, though, is P minus K prime. And so these are the two Feynman diagrams, and you have to add them together. And Weinberg actually did in the book the traces, and the traces get rather complicated because you have to add together the two different amplitudes and then square, and that makes things more complicated. Anyway, the S matrix amplitude then is over here, this vertex. To do this vertex, what we would have would be U bar of P prime, S prime, and we can give it an index, boy, this is almost invisible. Okay, it's beta prime. And we divide by 2 pi to the 3 halves. So I'm just following the Feynman rules the way Weinberg describes them. So this vertex here, out comes a photon, and it has polarization vector, and since it's a final state photon created, we have a complex conjugate and a prime because it's K prime. And it has again a 2 pi to the 3 halves, and then a square root of 2 K prime 0. So that's the energy. And that will describe in both this term here works either for this line or that line. Works both for this line and for that line. This factor works both for this line and that line. For the two intermediate lines, we're going to have 2 different terms. For the 2 incoming lines, we're going to have, for example, the initial electron is UPS and a subscript alpha. Again, we divide by 2 pi to the 3 halves. And then we have an incoming polarization vector, and we divide by square root of 2K0. So we've done all the external lines, and the external lines are the same in both Feynman diagrams. But now, what we do is we integrate over d4 q. Q is this momentum here. And we then put in the electron propagator, and the electron propagator is minus I over 2 pi to the 4th, and then minus I q slash, remember the slash notation, A slash is equal to AB gamma B sum on B from 0 to 3. So this is minus q slash plus m over q squared plus m squared, and there's a minus I epsilon, but it doesn't matter because this thing isn't 0. I'll stick it in the minus I epsilon. This is alpha prime beta, and now what we have are the 2 terms. Let me see.
are we missing an extra 2 pi to the 3 halves? Shouldn't there be 4 factors of 2 pi to the 3
Yes,
halves?
thank you. This should be another 2 pi to the 3 halves. It's, let me give you a candy. And now, what are these other 2 factors? I would normally have written the thing as 2 different electron propagators, but Weinberg instead writes it this way. We've got then these 2 vertices, and one vertex is E 2 pi to the 4th gamma nu beta prime alpha prime. And so Weinberg is following his rules religiously here. So this is the, in this case, this term is this vertex. And because we have this vertex, we also have to have this vertex. And this vertex is E 2 pi to the 4th gamma mu, and it's beta alpha delta 4th of Q minus P minus K. So that's this term, and then we have to add in this one. And it comes in with a plus sign, and the reason is that the fermions are in the same locations or play the same role in this diagram as in this diagram, and so it's actually a plus sign. Whereas you remember in E plus E minus scattering, there's a relative minus sign because the fermions look as though they're playing the same role, but actually they're not in the 2 diagrams. Anyway, this one then is, now we're doing this diagram, and we have E 2 pi to the 4th gamma mu, and once again beta prime alpha prime delta 4th of Q plus K minus P prime, and then E 2 pi to the 4th gamma nu beta alpha delta 4th of Q plus K prime minus P, and then a final bracket. So these, following the Weinberg's statement of the final rules, this is exactly what one gets. This term here is says that Q is P prime. That's curious. Q is P prime minus K. Right, so this Q is P prime minus K because when it grabs K, it becomes P prime. That's one way of thinking of it. In the other case, it's well, the other Q is the other delta function is for the other vertex. Anyway, what we then get is, if we do the spin sums, and I'm just describing what Weinberg got, it's minus I E squared delta fourth of P prime plus K prime after doing the integral. Of course, when you do the d4th integral, Q gets set to P plus K in the first case and to P minus K prime in the second case. And then energy momentum conservation gives us this, and one's left with 2 pi squared square root of 2k prime 0, 2k0, a u bar of P prime and S prime, and then E slash star prime minus I P slash plus K slash plus M being the electron mass, P plus K squared plus M squared, E slash, and E slash is E mu gamma mu, E being the polarization vector. Remember the polarization vector is transverse. And then this is E slash minus I, P slash minus K slash plus M over P minus K prime squared plus M squared, E slash star prime, and then finally U, P and S. And you see the spinners are playing a very simple role here. There's just one spinner going in and one spinner going out. They're both electrons, so we don't have any V's or V bars. And the simple way in which the U's enter is related to the fact that these come in with a plus sign. Now, to actually proceed further with this is really hairy, because you've got to take the absolute value squared of this, and it is very, very complicated. Some things do simplify, though. These denominators are much simpler than they look, because P plus K squared plus M squared, well, P squared is P is the momentum of the electron coming in. It's a physical electron, so P squared is minus M squared. K squared is the momentum of the physical photon coming in, so K squared is 0. And so we have 2 P dot K plus M squared, so this is actually equal to just 2 P dot K. And similarly, the other one, P minus K prime squared plus M squared, is just equal to minus 2 P prime dot K. So some of this is much simpler than it looks, and but the traces are formidable, but of course there are rules for doing them, and in the modern era they cause much less trouble than the chairs in this room. I think maybe I'm going to try to erase the boards. It may be that I'll have enough time to do both sides of the whiteboard and then have time left over. We have a new eraser, so the support erasing is easier than it used to be. So is there a question? I haven't been a whole lot of questions. All right, while that's drying, remember in Weinberg's notation, this S is minus 2 pi I delta fourth P prime plus K prime minus P minus K times M. I don't know why I wrote it as curly M. I think that was a mistake. And, all right, I'll write down what M is, but I'm not going to do the traces in detail. Of course, anything like complicated traces or computing Einstein or Ricci tensors, weird metrics with computers, these things are really quite easy to do. It's just, if you try to do them with your head and your fingers, it's another matter. Square root of K0, K prime 0, U bar, P prime, S prime, E slash star, prime meaning K prime and so forth, minus I, P slash plus K slash plus M, E slash over P dot K. So these denominators, these propagators become much simpler. And the rest is minus E slash minus I, P slash minus K slash plus M. And this is divided by P dot K prime. And then we have an E slash star prime. And a U, P and S. So that's the expression. You then take the absolute value square of that. And as I said, it's a few microseconds on a computer, a few days if you try to do it yourself. You then get d sigma is 2 pi to the fourth, the relative inverse of the relative velocity, m squared delta fourth of P prime plus K prime minus P minus K, and then dq P prime, dq K prime. So this is similar to what we were doing this afternoon, well, earlier this afternoon. The formula for this U, let me just mention where you can find it. In general, it's for an arbitrary two particles in the initial state, which is normally the case. The general expression is Weinberg's equation 4.17 of chapter 3, and the answer is that U is equal to P dot K absolute value over P0, K0. Anyway, he does this in the rest of this in the lab frame, and so P, for the rest frame of the electron, and this is, he's thinking of Compton's original experiment where Compton had X-rays coming out of, I guess he had some radioactive sample that was producing X-rays. had a comment. I don't remember. It's been a while since I read his paper, which I recommend, by the way, at least the beginning of it. P0 then is equal to M. So just to finish, in other words, what he had was he had a source of X-rays, and he was shining them on, I suppose it was hydrogen in the gas, and then detecting the photons that were scattered. The relative velocity is 1 since the electron is sitting at rest, and or relatively speaking, is moving non-relativistically compared to the photon, which is relativistic. Anyway, so U is equal to 1, and that's the relative velocity. And there are various other things that happen in this frame. Let me, I think, I'm going to skip down to, I think I'll just skip down to well, I'll do a little more. Let's see. We first of all have omega, that's K0, that's length of K, and that's minus P dot K over M. Omega prime is minus P dot K prime over M, as you can imagine. And once again, one has this delta function, and in this particular case, it's delta of the square root of K minus K prime squared plus M squared plus omega prime minus M minus omega. So that's the conservation of energy delta function. And so if you differentiate it with respect to K0 prime or to omega prime, what you get is that this is equal to P prime 0 omega prime over M omega, and you're left with delta of omega prime minus omega Compton of theta. And omega Compton of theta is omega plus M over M plus omega 1 minus cosine theta. Okay, and the final d cubed K prime, of course, is omega prime squared d omega prime d omega, and so finally d sigma is equal to 2 pi to the 4th m squared, and what we're left with is p prime 0 omega prime cubed over m omega d omega. And here p prime 0 is m plus omega minus omega prime, as you'd expect, because that's just conservation of energy. And so the hard part then is doing the traces, so I'm going to skip that. And these traces were, we had to do 4 traces to do electron-positron scattering. Here, one has 1, 2, 3, 4, 5, 6, 7, 8 traces of 8 gamma matrices. And then one gets an enormous number of terms. And let's see. So once again, we're doing these things in the lab frame, and if you do the final, again, we're going to be averaging over initial spins, the initial spins and of the electron, and summing over the final spins of the electron, and what one gets then is sum, 1/2 sum over S and S prime of d sigma, and what one gets is e to the 4th omega prime squared over 64 pi to the 4 pi squared m squared omega squared d omega, and then a factor. And the factor is one you may have seen before, because this is a famous formula: omega over omega prime plus omega prime over omega minus 2 plus 4, the dot product of the polarization vectors of the photons. And notice there aren't any complex conjugates there. You can take the polarization vectors real if you want to. You don't need to imagine that they're complex. And this is the formula that was derived, believe it or not, by more difficult methods, because they didn't have Feynman diagrams then, but by Klein and Nishina. So this is called the Klein-Nishina formula for the differential cross-section. And if we go further and average over the polarizations of the photons, and here I think I'll flip this over. Although, in view of the hour, we've only got 5 minutes left, let me move this and leave this visible, because it'll be kind of relevant. So what I'm going to do next. What we want to do is we have to sum over the final state.
Hey Kevin, the board's kind of blocking the camera.
What?
It's kind of blocking the camera.
Yeah. And if we sum over the final state polarizations, E prime I, E prime J, this is delta Ij minus K hat prime I, K hat prime J. And then what one gets is 1/4, and now we're summing over E prime, SS prime. So we're summing over, we're not measuring any polarizations. D sigma, this is then E to the 4th over omega prime squared, D omega over 32 pi squared, m squared omega squared, and then again this Klein-Nishina expression, except that now this just becomes a cosine, and theta is the angle between the two photons. So you have photon in K, photon out K prime, and this is the angle theta. And this is the electron that's not really detected, at least not typically. If one goes to in in the non-relativistic limit, where the photon is of, let us say, keV energies, low keVs, dozens, a few keVs, several keVs, maybe tens of keVs tops, then these two terms are equal. That is, omega and omega prime are essentially the same, and so you have 2 minus 1 and you just get 1. And so this becomes 1 plus cosine squared theta in the non-relativistic limit. And in that limit also, if we do the integral, so we go to the non-relativistic limit, do the integral, you then have to integrate 1 plus cosine squared theta d omega. Well, this is the integral we just did before, and so this is 2 pi from the phi integration. We then get a 2 from that and a 2/3 from that, and altogether this is 16 pi over 3. And the total cross-section then is what's called the Thompson cross-section, namely e to the 4th over 6 pi squared m squared. So this is the cross-section then for low-energy photon scattering off an electron, where this, of course, is the mass of the electron. And so this is, again, for a single free electron. And in the case of Thompson scattering, I think the electron wasn't free, but on the other hand, the energy he was using was so high that the orbit of the confinement of the electron, or the motion of the electron in the atom was not significant. On the other hand, if you're talking about photons scattering off electrons in atoms or molecules, then the energy levels of the atom and the molecule are important, and the scattering is off the whole atom or molecule. And that, by the way, is kind of relevant because the wavelength of visible photons is something like half a micron, which is huge compared to the size of a molecule. Consequently, the electric field of the photon affects the whole atom and molecule essentially simultaneously. In fact, that's the approximation one uses in atomic scattering. And I think that's one of the nicest problems in advanced quantum mechanics, is to consider the photons scattering off atoms, and then one sees that if since you're interacting with the whole molecule, you add up the scattering off every charged particle, and nuclei are not so important because 1 over m squared doesn't matter in the case of the nucleus. I mean, it's just 0. But you then add all the amplitudes and square the result. And so if the molecule has lots of levels, like CO2 or methane or water, you get global warming and fires in California and wind in New Mexico. All right, I guess we're done unless there's a question. Oh, Jesus! All right, does anybody else ask a question?